için teşekkür ederiz. So I will switch to English since that we started recording. So it's my great pleasure to host Utku Günay Acer. He's a principal research scientist at Nokia Bell Labs, and he's also a member of Sabancı University, class of 2004, with a degree in telecommunications. He then joined RPI to pursue a PhD degree, which he obtained in 2009. And before joining Bell Labs in 2010, he was a postdoc at INRIA Sofia Antipolis. His research interests broadly lie in distributed systems, and more specifically, he's interested in the system and algorithmic challenges in multi-sensory sensing in edge computing systems. Yeah. So, Utku Hocam, the stage is yours. Thanks a lot for joining us today.
Thank you. It's my pleasure. It's my pleasure to be here. I wish this was in person. I wanted to do this. I actually wanted to do this in person, but is it for me? This message? Okay. So but we couldn't really make the arrangements back in the summer when I was in Istanbul. Well, this is Thursday 24. I guess I want to start with extending my best wishes to all the teachers today. But my talk is going to be about our sensory intelligence platform for edge devices, which we call SensiX. And then, after giving an introduction of SensiX, I will talk about Lingo, which is a realization of SensiX for a smart city solution. The last two decades in the computing have been dominated by the cloud technology. Where the web companies, web applications quickly scaled out and service a large number of people across the globe. But recently, in the last few years, we are seeing a new paradigm shift. In the future of the computing will be driven by applications built by AI/ML, and these applications come with their own characteristics. And these are orchestration for these devices, for these services can no longer depend only on the performance, like throughput, but they should be increasingly driven by the accuracy of the underlying AI/ML models. And in order to achieve this feature, we have to move some of the intelligence back to the edge from the cloud. But this brings up its own challenges, because when we are talking about the edge, we are not really talking about a homogeneous computing environment. Instead a large degree of heterogeneity. And with this a particular challenges, auto configuration of tuning devices. This is an example for a network of smart cameras, where AI-enabled cameras capture the stream and then transmit it through the internet to a video processing cloud, where the inferences on the captured video feeds are performed. So if you consider when you consider the high quality of the videos, then going from all the way from 4K to 20K, these are large high bandwidth streams. So streaming these, transporting all these streams from the source to cloud location is going to be very difficult. So therefore, we have to face the challenge of localized and real-time execution of AI models, where at the edge where the data is generated. So these systems should be highly efficient, not in terms of just the model execution, but also in terms of latency, in terms of bandwidth. Obviously we cannot send all the raw data, all the video streams from the camera to the cloud. So we have to be selective about what we are uploading to the cloud. We have to be mindful about the privacy. We have to protect. This is not just a application requirement. This is also a legal requirement now. We can, particularly in Europe, we have to be very careful about what we are doing with the raw data, and also we have to be availability. We cannot really rely. The connectivity between the cloud and the AI cameras can be reliable, and we have to provide availability regardless. So, what are the feature of so we have to move the intelligence to the edge, but it is not like, we cannot really just dump our ML models on the edge devices and execute them. So the feature of intelligence at the edge should support multi-devices, because obviously the coverage, the scope of a single device is not nearly enough. And these systems should support multiple modalities, multiple sensor modalities, from the audio to video and to environment sensors. And also they should support multiple models. But on the other hand, the existing operating systems are not really optimized for such services. They don't really provide adequate abstractions for ML applications. They don't have the energy awareness, and the runtime is not really optimized for the AI ML applications. So to design a platform for edge intelligence, we are facing a few challenges. One of them is, our design should center on multiplicity, not just in terms of the sensors, but in terms of the models, to provide better learning opportunities. Design should take into consideration of data and device heterogeneity. So even if say for in the camera networking, even if we have used different cameras with different encodings, different resolutions, the models should retain their functional behavior. And then and the compute environment, we have to also consider the compute environment is different, right? They think the accelerators might not be available across all devices. So a platform should take this into consideration. And then we cannot really rely on web scale performance metrics anymore. We have to, the runtime efficiency should consider on model execution, despite the heterogeneity in the accelerator. And we have to change the way we have to change our programming paradigm, and we have to shift towards a event-driven application, where we have to turn sensory data, raw sensory data, into contextual events that trigger execution of application logic. Also, we have to be able to identify new sensors, new models, and we have to these sensors and models should be deployed and upgraded with minimal effort. So our solution to this is a platform which we call SensiX. SensiX automatically discovers and transforms collections of raw sensory streams into high quality and high reliable contextual streams. So to designing SensiX, we follow the modular design with service-based architecture in mind. The applications are no longer packaged together in monolithic blocks, but instead we have divided applications into logical components. So, we say, so in each component by separating it, we allow a component to be reused across multiple applications. So this gives us 2 orders of magnitude gain in the deployment time, in efficiency, and in network efficiency and the compute efficiency. So this presentation was actually prepared for a demonstration, but I'm afraid I'm at home now, and I don't have the equipment to show you the demo, but instead I'm going to present you these components. So the first component we have is the sensory interface, which automatically discovers and configures the sensors throughout their life cycle. It provides a flexible interface to the other components, for example, the models or the system scheduler. And to provide the sensor data, it deploys a efficient raw data store that's hidden behind a local API that the components can access. And it also provides key abstraction. In this more key abstractions for the reusability. This component also performs basic data preprocessing functions, and also allows applications to access these also to be both preprocessed and the raw data from the sensor input. So the model, we deploy the models in separate containers. So we deploy a separate container for each model in the device, and the model builder basically creates these containers automatically based on the developer input. So it constructs the model images using the user input. I'll come back to this developer input. It also automates the pipeline construction all the way from starting from the preprocessed data captured by the sensor interface. But this component handles feature extraction and other post processing examples, and say, for example, scale by preprocessing. For example, it can include changing the image resolution to the needs of the model and then converting back to the what the original image dimensions were. And it also provides fine-grained model serving. And this component also includes a feature cache. So the extracted features can be reused across multiple models through this component. It also includes a few other components like the sensor selection, translation, acquisition, to further improve the performance of the models. But I'm not going to go into these components. So the execution runtime is the heart of the system. It provides it facilitates data management, data sharing across multiple components, and it basically schedules it provides a scheduler for the model containers. It provides resource monitoring, profiling. If necessary, it unloads the current models and loads new models to the memory. It uses diverse scheduling policies. For example, it uses reinforcement-based learning, reinforcement learning-based schedulers for different models, and it is basically drive the system-wide performance of our system. And finally, we have a query builder. The query builder is where the developers and users face the system. It provides a number of APIs. These APIs can be used to deploy new applications, new models, new functionality to the device. It also manages the microservices where the model inferences are interpreted by the applications. It provides multi-model query service. It can be, the queries can be answered by text, chart, or streams. And also, it provides the API for the other components, like the external users, the external developer, the maintainers of the system can manage different components through the APIs that's provided by the query builder. So we use a document-based application and model execution for bootstrapping and runtime of our models. So developers, when deploying a developer, we ask the developer to provide us 4 files. Because this is a query system where a user can make a query, certain queries. So we start with the developer to provide us a list of questions that their application can be used to answer, and also answers that correspond to these questions. And the answer that should be answer templates. The developer provides us with answer templates, and these templates are likely use model interpretations of model inferences. It can be directly an output of a model, but it can be also a function of. It can be these variables can be derived from the model output. And these derivations from the model output are performed in application functions, which we call, the developer provides a codelet, which is basically a list of functions that needs to be executed on the model output or the sensory input. And finally, we ask the developer to give us a model manifest file. So the developer basically gives us from a model store, it gives us the model that the application use, what the type of input for the model, what kind of input the model requires, what is the output of the model, also what is the frequency, what is the frequency at which we have to sample the input, and also what is the latest, how long we can keep the inferences. So this allows us to reuse the model for across multiple applications. For example, if we use if 2 applications rely on object detection, for example, one application we typically use is when we demonstrated car park monitoring. So for example, detecting the cars in a video stream to understand the remaining capacity in a car park. So we have to detect the cars and how they move in a parking lot. So, and then in another application, we detect the number of people in a room and where they are located for event organizers. So these typically these two applications, even if they may use the same object detection model, if you prepackage them, you have to deploy two object detection models in two separate execution environments, and then that basically leads to redundancy. Instead, in our case, because it is modular, the same application, the same model output can be used for different applications. So when a query arrives, the query extracts what we do is the query builder extracts the corresponding answer template from our answer Q&A data store. We derive the answer template based on the question and run the corresponding codelet to prepare the answer, and then we serve this answer back to the user using the format they require. Because while some questions are served with text, some can be, say for example, in the case of object detection, it can be served as a video stream. So this is a very short introduction of SensiX. And now I want to talk about Lingo, which is a realization of SensiX for smart city solutions. So there is a bit of a confusion. There might be a bit of confusion. It's like the name of the system I'm going to present is Lingo, but this was prepared within the context of Essence project, which was a project funded by the Flemish Innovation Agency in Flanders, Belgium. It was a multi-institution project with partners from academia and other industrial organizations. So this is the core of the project was to increase the citizen engagement with smart city solutions. So this has always been a problem for smart city applications, smart city services to start off. There are many smart city solutions. There is one prominent example in the city I live in Antwerp. But when you look into population, there is a limited citizen awareness. These solutions typically have limited coverage in terms of limited spatio-temporal coverage. Also, each service provided by the smart city platform is basically provided using a different app, and that leads to, as the services increase, that leads to more apps overload, which is also a factor that which also keeps the engagement down. So in this work, we were interested in hyperlocal information. By hyperlocal, I mean the type of information that's relevant only at a particular place at a particular time. With a very limited scope, very limited spatio-temporal scope. This can be, for example, the level of allergens right at that spot. There are other services, for example, that give you a rough estimate of the allergen information throughout the day, but this is more like, okay, what is the allergen information right at the moment? What is the pollen count in this park where I'm at the moment and at this time? Or again, in the context of Belgium, it can be the schedule of the weather. The schedule of the utility workers, such as the postal workers, the garbage collectors. This is still, this is very, well, at least in the context of Belgium, this is really important because, well, we have the garbage collection only once a week. So if you miss that, then you are basically, you have to keep your trash for another week, which nobody wants. So even though you may have a rough idea about the schedule, what time they might arrive, there is no platform that can tell us or if they have arrived yet, or are they going to arrive in the next hour or so. So we have done a well, we didn't really start with okay, let's just serve people hyperlocal information, but instead we wanted to understand whether hyperlocal information is essential or not. So to do this, we started with a user study, a multi-phase user study that includes to understand what whether people are interested in ultra local information, what type of information they need, what is the interaction modality they would prefer, and etc. So to understand this, we had a multi-phase user study. We started with an online survey of Amazon Mechanical Turk up to 2,000 participants to understand if the interest in in this kind of information is global or it is only a local issue. We dive deeper in a more culturally constrained case with 21 participants from Belgium from our institution, and then we followed up with a local workshop with 20 participants from outside Nokia. So what we have, the results we have seen. Okay, the results we have seen are typically consistent. The number down is wrong. It should be 60%, but still. So what we see is 90% both in the survey, online survey, in the interviews. Roughly 90% of the participants notified us. They told us they would like to get more information about their surroundings. On the other hand, only about 11% thought the methods they use currently are sufficient. These methods can include the word of mouth, social networks, bulletin boards, etc. And we asked the users also the type of modalities. Actually, this is as I said, this is wrong. The most popular modality was a voice-based interaction with 60% of the users, but using an app also, an app to reach this kind of information was also a close second. But again, with these results, throughout the studies, the results I would like to share, we don't really treat them as final or generalizable. This is more, these should be interpreted more in the cultural context. Oops, sorry. So we asked the users also what kind of information they would like to access. So from these answers, we had this. We categorize the type of information into 4 categories. They can be related to health, like the allergen information, the safety. The safety, not safety as a overall idea, but safety at the momentary safety was very important. But and then the people were interested about their community, their neighborhood, also the infrastructure like the roadwork and their schedule. So when we then through the workshop, we tried to come up with what actual questions. We understood the categories, but then we wanted to understand what actual questions we would like to the people might be interested in. So these are so we came up with through the workshop we came up with 20 questions. Again, these questions are within the context of Belgium, actually within the context of Antwerp, actually. So we came up, we saw that, you know, there are two types of questions, actually. One of them is, you know, the questions with static answers, like is the swimming pool open today? It doesn't change. You know, these questions you can find the answers you can find through more traditional channels. But on the other hand, there are questions with the static, with the dynamic nature, and to find them, you have to have some contextual information. So we have to rely on AI ML models to understand that context, this location context. And to get this context, we have to perform vision sensing, acoustic sensing, and you know, to understand the ambience around, and then also the environment sensing. So, then this is where the SensiX system comes in. So we actually use SensiX to create a live log of the urban place where they are located. But we augmented SensiX with some crowdsourcing. This crowdsourcing part was from a previous project we had with Belgian Postal Office, where we use their workforce as a crowd worker, as crowd workers to enter the information. So whenever they have where there is any, well, this typically refers to this static questions. Whenever we provided the postal workers with some smart watches, and they use this to enter some crowdsourcing, some questions, static questions, and they would provide the answer to it, and then this would feed into our SensiX system. But today I would like to talk about because this is an AI seminar, so I'll be more focused on the AI part where we use SensiX. So our key solution is embedding these SensiX observers into local landmarks, urban landmarks in a city, and so these observers have the complete knowledge of their surroundings, and then they would infer the community and the location context through ML models. So this is basically a rearrangement of the the knowledge builder is basically what we have for the SensiX observer. So yeah, this is again, this is a recap of the SensiX for using multi-sensory as a multi-sensory perception engine. So for this prototype, for the system, we used an AGX devices as our SensiX observer. We equipped this device with a smart camera that capture high quality video, a microphone array, and an environment sensor to perform again environment sensing, vision sensing, and acoustic sensing. And then in the third phase of this work, we also looked into how we enable the interaction between the observers and also the users. So to facilitate the users, we developed two agents that reflects the user's interaction modality. One of them is basically a voice assistant, like what we use in the theory, but instead these are standalone devices. This is not really connected to our SensiX observer. But instead, and then we developed an Android app. The first app uses basically voice modality for receiving the questions and answering them when the user can question through voice. And then the answer is played back to them. But in the app we have the textual interface. Both of these devices are connected to the internet, so we use a cloud-based NLP engine to match the user's query to one of those 20 questions that we use our system to answer. And a key decision we made for this one is we want our observers to be completely offline. So they are basically standalone devices. And in order to make a query to these devices, we have to be within their immediate vicinity. So not only the information is hyperlocal, but also the query and the application, querying system is also hyperlocal. So this is so we use a covert communication mechanism based on Wi-Fi, but so where our SensiX observer acts as a Wi-Fi access point, but we do not require the users to actually connect to these access points. Instead, the interaction happens through Wi-Fi management frames, where we use actual metadata to typically use management frames to discover the networks or associate with the network. But instead, we define a special kind of management frame to carry a payload of up to 2.3 kilobytes. And since the questions and the answer are typically based on the text for this case, because in this particular case we are not really using stream as a query output. Mostly all the query results are given in text. So this is 2.3 kilobytes is more than enough, even if the agent where we use to interact with the SensiX observer may actually convert to a speech, but still the query result is always a text. So we have an extensive evaluation of the system across 2 papers. One of them, the core paper of the SensiX, is currently under review for a journal. I believe it is TMC, but I'm not entirely sure. And the paper that describes the Lingo and how we can use SensiX as a voice assistant for a smart city solution is represented back in September in Ubicom. And I would like to refer to you to those 2 papers to have a in-depth analysis of performance evaluation. But now I would like to talk about our future work, what we plan next. So in both systems, in both cases, we consider the SensiX platform as standalone devices, which gives us limited scope, limited coverage. So an obvious way to increase our coverage, increase the scope of our solution is to make these devices collaborate. So this is going to be our basically our future agenda, but not necessarily on the scale of SensiX, but we are now going more into the personal computing space, where we use multiple devices, multiple smart devices with compute resources, with however small accelerators. How we can create a virtual computing environment around the person, around the user, and how we can discover available devices. This includes we are thinking of how such a system can be architected. This includes discovering the new devices and sensors, and how we can decentralize execution, because one device, so if we have a heavy model, one device is not enough. One accelerator will not be enough. How you can distribute the execution of an ML model across multiple devices, and also whether you can use how you can reuse an accelerator across different models. So the accelerator sharing is also a part of the issue. So in order to help us realize this agenda, this is an invitation to your the PhD students and master students who are in this call. We are currently receiving applications for our summer 2023 internship program. And if you are interested in distributed systems, embedded software, ML accelerators, also, we also have groups that work in theoretical machine learning for the federated learning. And then we also have the they're still a software group, but they are more they more tend to the hardware, the device form team, where they generate new forms of devices. For example, if we can equip the equip the headphones, the wireless headphones with ML accelerator, and to even further the on-device ML execution. So if anyone is interested, you can send me an email, or you can directly contact my colleagues here, Diana or Fahim, to state your interest. And that will conclude my talk. And I think I have now time to answer your questions.
Thanks a lot, Utku Hocam, for the great talk.
Thank you very much, Utku Hocam.
Thank you.
I have a question. So in your current platform that you have presented, do you have plans to utilize federated learning?
Yes, but in the this is a bit tricky. In the current we are working on new platforms, and federated learning is definitely I'm not working on federated learning, but I have colleagues who are they're actively working on federated unsupervised learning mechanisms, and they are of course interested in deploying their solutions. I'm not sure whether they are going to do this in the SensiX environment, but on the say even smaller scale, like the wearable devices. But yes, we are going to deploy my colleagues will deploy their federated learning solutions to these platforms.
Thank you.
Maybe I can ask a quick question if there are no other questions. Yeah, I'm actually curious about how much of it is developed in-house, and how much of it is external services.
Yeah, say we didn't do model engineering. We used off-the-shelf model, but aside for that, everything was built in-house.
So for instance, you had this host operating system. Is there something like a Nokia operating system?
Okay, yeah, that's well, at the moment, no, but yeah, for the AGX device, no, we started with Ubuntu, of course, but I mean, it is not just the we built upon Ubuntu, but it is not what you get from the an Ubuntu image. But the second generation of devices we are working with, the wearable devices. For example, we are now developing a what we call earbud. It is basically, and we are using two headphones that connect to each other through wirelessly, but they also house each house a tiny ML accelerator. There is not an operating system for that. So we are well, again, we are not starting from the scratch. Of course, it is probably going to be based on our thoughts. It is one of the topics that we expect intern applications for. Mm-hmm. But then our involvement, our development will be more. We have to do more developing in that in those devices.
Okay. Yeah, I was also curious about the NLP engine. You said you are using a cloud NLP engine.
Yeah, NLP.
And it's just to classify the questions into...
Yes, so it is basically intent matching. It is we are using dialog flow. It is just intent matching. It is not really the core of our project. So it is. So we try to do that on device too. NLP. We try to deploy the NLP engine on device. So we use some off-the-shelf NLP model, but the memory wasn't enough. We thought, because these are user agents, we can afford them the connectivity. So this is how we deployed them. But deploying NLP engines, if you deploy an NLP engine on however strong the device is, then you don't really have any memory enough for executing any ML models.
Yeah. I think there's a question from Abdul Razak. Yeah, go ahead.
Okay, thank you. Thank you for the presentation, first of all. I have a question in mind. You talked about SensiX and one of its applications that you tried. For the SensiX itself, the platform, is it public for usage so I can use it? And the second part of my question, is it the output of the platform, is it a trained model that I'll get the parameters and I can use? Or it's only that you will train a model for me, I give it input, you give me output?
So let me start with the first question. Right now, our code base is it is not open at the moment because we are in the process of commercializing it, commercializing the solution. So it is not open at the moment. So for SensiX, the model is okay. This is I'm not sure if I understood it correctly, but so so there is this demonstration, of course, but there is also that's not necessarily to but that's not really the if for example commercialization happens, one of the solutions we would like to pursue is to actually deploy a model store for developers. Right now, the models are deployed in containers. So say, for example, I might say if you're familiar with YOLO, for example, object detection, an application might draw, for example, bounding boxes of detected objects on a video stream, right? That might be your solution. But in our case, we want the YOLO to produce only the model container to produce only the list of the bounding boxes. The bounding boxes, the type of object, and that's it. And if your application, for example, if you want to just count the number of cars, there are 5 cars, you don't have to draw the boundary box, right? You just count the number of detected cars. But if another application wants to have a stream, then that can do the stream. We just want to separate this application logic from the model execution. The model inference is just the model output, just the list of bounding boxes, detected objects, and their confidence.
Okay, thank you. So the output is the inference of something that I need. It's not like parameters of the model. I will not be able to access the model itself. So there is no risk on the data that you are processing.
No,
for example.
No. Okay, so you are talking about the user query. No, the user doesn't really. The user only can make a query about the type of the questions that the developer provides.
Okay, thank you.
So we wanted to have this an open model where as long as we provided a format, but As long as it is the developers stick to that format, they can introduce their own applications. And yeah, in terms of the models, we want to have this model store, but also they can, if you can containerize the model, with the, well, it is not that difficult. We also have some processes to containerize the model execution. But for example, we might have to use, if you want your model to run on GPU, you might have a different container than the model running on TPU or CPU. So there are some nuances. So we want to have this model store to address all of these, but it is not there yet. But it is one of the venues we can go after it becomes a commercial product.
Okay, thanks for answering and thanks for the presentation again.
Thank you.
Any other questions? Okay, then let's thank the speaker again. Thanks a lot for
thank you. Thank you for
us.
having me. Thank you for having me.
And hope to see you in
yes,
person, maybe sometime.
Yes, me too. And I'm always we always welcome new interns, and really I strongly encourage your PhD students to apply for internship. And who knows, maybe it will turn out to turn into be a good collaboration opportunity.
Yes. Okay.
Okay.
Then see you everyone.
Yes.
Next
Thank
Thursday.
you, everyone. Yeah. Thank you.